Now that we understand the meaning of electric potential and electric potential difference, we'll now begin our unit on capacitors and capacitance. So what I'm holding right here in my hand, this is a 1 farad capacitor, and we'll talk in great detail about the operation and the construction of capacitors, but suffice it to say for now that a capacitor is two conductors, two conducting plates separated by an insulator. In other words, an insulating medium is between these charged plates. And capacitors are electronic devices that store charge and therefore electric potential energy. There's many uses, many functions of capacitors. I'm going to show you one here. So right now this capacitor is in an uncharged state. But I'm going to show you that by doing a little bit of work on these plates here, we can transfer charge from one plate to the other. Now I could charge this capacitor with a battery, but I'm going to choose to use this hand crank generator just so you can visually see the work that I put into transferring the charge from one plate to the other. So you can see that I'm doing work here. And I will disconnect the hand crank generator here. And this capacitor is now in a charged state. It is storing charge and electric potential energy. One of the functions of a capacitor is to be able to provide large power surges. That is, to release a lot of energy per unit time. And I can show you that here when I connect this to this bulb here. That you will nicely see the charge and electric potential energy stored in it as the bulb lights. What you'll notice is that this capacitor, unlike a battery, does not maintain a constant potential difference, and that is why very quickly the bulb will dim and go out. So one of the functions of capacitors is to produce large power surges, as we'll talk about in some of the upcoming slides. At this point in the course, at this point in our study of electrostatics, we know a lot about how to calculate electric fields and the electric potential for various charge distributions. So what we're going to take a look at in this unit is applying some of this physics that we already know to a specific, very important technology, what we call a capacitor. So in the most basic sense, what is a capacitor? A capacitor is nothing more than two conductors that is separated by an insulator. And we'll see later in today's presentation that we call this insulator a dielectric. And when we talk about why is this technology, why is this electronic device we call a capacitor so important? These are some of the purposes, why capacitors are used in technology. So they can store charge and therefore electric potential energy, and that charge and electric potential energy, it not only can be stored, but it can be released quickly. So by releasing it quickly, you can produce as well as prevent large power surges in circuits. Capacitors can also be used as time-sensitive triggers in DC circuits, as we'll see. So these are not all, but these are some of the main reasons why capacitors are used. Now, to get a little more specific, to look at some more specific examples, we'll take a look at some uses or applications that I think you'll be a little more familiar with. So when you talk about charge storage in almost all electronics equipment, radios, televisions, and certainly at some point in your life, you've probably looked inside, whether it was broken or being repaired, some piece of electronics equipment, whether a computer, radio, television. And what I'm showing you on the screen here, you see this is an example of a capacitor, used to store charge and electric potential energy, and in this case, to prevent power surges in a circuit. I include this
example here, not because it is so important, you know, in our modern day technological society, but it's one where you can, okay, nicely see the purpose of the capacitor. This is the shake flashlight, okay, which you can take on a camping trip. It does not require any battery. And by shaking it back and forth and moving this magnet in and out of this coil of wire, you can induce a current. This is a phenomenon called electromagnetic induction. We talk in great detail about later on in the course. Okay, but my purpose of including it here is because there is no battery, but what you see over here is a capacitor. So as this charge is being moved through the wire, as a current is being created, that capacitor can store some of that charge, okay, which can then be used to power, okay, a small light. Okay, a starter system in an automobile. Think about it. Okay, an internal combustion engine starts off at rest, and in order to get your car to be able to take you places, you've got to get that, okay, internal combustion engine to start rotating at about 3,600 revolutions per minute. Okay, now this is a heavy piece of equipment, and you know from Newton's first law that, okay, objects at rest have this tendency to want to stay at rest. How are you going to get that very heavy object rotating quickly? Well, a 12-volt battery in a car simply cannot produce enough power to be able to make that engine start turning. Okay, it has simply too much inertia. So inside, okay, the circuit, okay, for your starter system of that automobile will be a large capacitor. So the battery can slowly charge that capacitor up, and that capacitor, it can release, okay, that charge very quickly. Okay, release that electric potential energy very quickly to provide a boost, okay, a surge of energy to be able to get that engine to turn over. It certainly can't maintain it, but it's capable of producing a lot more power than a 12-volt battery can. You know, other examples, think about the dryer, a fully loaded clothes dryer. Same story. You're going to have a fairly large capacitor in there because starting off at a state of rest, to get that dryer drum, okay, to start turning requires, okay, a lot of power. And that capacitor can provide an instantaneous large amount of power. Can't maintain it, okay, but it can provide it to get, okay, the dryer drum to start turning to overcome its initial inertia. A compressor for an air conditioning unit, same story. You're going to have a fairly good sized capacitor in there, okay, to help that compressor motor start as well. All right, so camera flash units, okay, especially in the old style cameras, you would see that to be able to light up a room required a lot of energy that a battery on a camera simply could not provide. So that battery charges up a capacitor, okay, and then that energy is released, providing you a surge of power, okay, and a very bright flash. And in the original cameras with these flash units, you may recall, okay, that it took a long time for that flash to recharge. You could not take pictures successively because capacitors take time to charge. A battery cannot produce a lot of power, so a battery can slowly charge the capacitor, okay, which can then release that charge quickly to produce a lot of power, okay, but that all takes time. Computer keyboards, but believe it or not, when you push a key on a computer keyboard, that key is nothing more than a capacitor. Okay, and when you push down the key, what you are doing is you are taking those two metal plates, okay, that are separated by that insulator, which when you push it down, you squish that insulator, you push those metal plates closer together, and as we'll see in a couple slides, that changes the property of the capacitor we call capacitance, okay, and that acts as a trigger, okay, in your integrated circuit, okay, and that trigger can, okay, in the form of, okay, zeros and ones can send a signal, okay, for something to happen, okay, like a certain key to be, okay, activated. Time delay device. Everybody knows your windshield wipers. Okay. When you put it on the time delay setting. Okay. This is an example of an RC circuit, which we will talk about in greater detail later. But for now, let's just suffice it to say that there is a capacitor in there, which takes a certain amount of time to charge, okay, and that's what causes the delay. And when that capacitor discharges, when it reaches a certain amount of charge, it can discharge. That can activate the wiper blades, okay, which actually require quite a bit of power, okay, to be activated. The capacitor discharges, takes time to charge up again before the blades can be activated once again. And we'll take a look at that specific circuit, okay, later on in the course. Pulsed power for particle accelerators. Well, at the National Ignition Facility in Livermore, okay, and let's take a look at this picture here. Okay, there are about 550 lasers that are aimed at a tiny deuterium pellet, okay, with the goal of instigating a fusion reaction using a technique called inertial confinement. And how do you think the sudden release of the energy from those lasers is simultaneously achieved? Okay, well, you guessed it. There's huge capacitor banks, okay, which are simultaneously activated to release that energy, okay, in a very brief amount of time, producing a high degree of power. This would be an example where, okay, the information is stored in capacitors in memory banks, okay, huge banks, and the capacitors have this ability to produce a lot of power, okay, by releasing a lot of energy in a very short amount of time. Okay, so memory banks of computers are basically capacitors. And this example I include because everybody's familiar with it, but when you look at the medical defibrillator, okay, that's used to revive heart attack, okay, victims here, this is really nothing more than a high capacitance capacitor. So when those paddles are placed on the victim's chest, okay, the capacitor can discharge, and a large but brief current, okay, then can be pulsed through the victim's heart with the hope of trying to, okay, revive the victim. Signal coupling. Okay, and this, okay, we will see here. Let's see if we can get a diagram here. Capacitors have this ability to couple and decouple electrical signals, as, okay, capacitors will allow AC, alternating current signals, okay, to pass, but they will block DC signals from passing through the circuit. And so in this way, okay, you have a nice way to, okay, filter, okay, certain signals in an integrated circuit. In addition, capacitors can be used to control voltage fluctuations in integrated circuits, which can be very damaging to circuits. Okay, so you kind of see here in this animated GIF that you have an AC current which runs into your capacitor, okay, but you get a smooth current out. Okay, it behaves as a sort of filter, okay, for okay, passing, only certain currents, okay, in this case, allowing AC currents to pass, okay, and it can be rectified, that AC current can be rectified into giving you a DC output current. So these are just some of the applications of capacitors, okay, and we'll talk about, okay, the physics of capacitors, okay, coming up, okay, when we introduce this property that we call capacitance. Now, when using analogies to explain phenomena, okay, you realize that all analogies are inherently flawed, okay, but sometimes they can be helpful, and I have no idea whether this is going to be helpful, okay, so you can take it or leave it, but okay, here goes. How is a capacitor like a toilet? Well, what we were saying is that turning a car engine over successfully requires great power in the form of lots of electrical energy supplied in that starter, okay, circuit per unit time. Just as flushing a toilet successfully requires lots of water power, really a high volume flow rate. Okay, that is a great volume of water per unit time. So conventional energy sources like batteries, like the 12-volt battery in your car, cannot supply sufficient electrical power to activate the pistons and get that flywheel rotating. Okay, in the same way that conventional plumbing sources cannot supply a sufficient water flow rate, okay, for water that's at atmospheric pressure. Certainly if you talk about pressurized plumbing, that's a different story, but that's not what you would find in the typical household toilet. Okay, so in that case, a battery can be used providing a relatively low power to slowly charge the capacitor, okay, in the same way that conventional plumbing can be used to slowly fill the toilet tank. Okay, so that, okay, when it's time to get the engine moving, okay, the stored charge in the capacitor is quickly released, okay, producing lots of energy, okay, per unit time, okay, lots of energy flowing in that circuit per unit time. In the same way, okay, when the toilet needs flushing, okay, the stored water in the tank is quickly released, okay, producing enough water power, okay, really volume flow rate to get those unwanted contents in your toilet to go down. Okay, so the analogy continues when I say that, you know, a toilet tank requires time to fill. Okay, because the water power, the volume flow rate for the water in a conventional plumbing at atmospheric pressure is fairly slow. It takes time for that toilet tank to fill. In the same way, when a capacitor is being charged by a low power battery, it takes time for that capacitor to be charged, okay, for it to acquire enough charge to be useful. So the capacitor will be the first electronic circuit component that we talk about in this course, but it certainly won't be the last. In fact, we'll conduct an entire unit on DC circuits in a couple of weeks. Now, in order to discuss and analyze circuits, we often need to draw them on paper. And for this reason, okay, we invent certain symbols to represent the various circuit components. These symbols are much easier to draw than the devices themselves. Yes, they will need to be memorized. Now, I'm going to introduce three circuit symbols here, two of which can be easily confused with each other. Okay, and that's one of the reasons why I'm choosing to discuss them now. Many more circuit components will be introduced into our lexicon as the course progresses. Okay, but for now, we're going to talk about these three. A DC voltage source, and I know, you know, we're going to talk in great detail about DC versus AC, so let's not worry too much about it at this point. But a DC voltage source is what you are provided with in the form of a battery. And the circuit symbol we use looks like this. Okay, now notice here that, okay, we have two parallel lines, but, okay, one line is longer than the other. The long line, by definition, is the positive terminal of your DC voltage source or battery. The shorter line represents the negative terminal. This is not to be confused with a capacitor. Now we're going to introduce two types of capacitors. A standard capacitor we draw this way. Notice that the symbol looks very similar to that of the DC voltage source. What's different? Well, for the capacitor, the two parallel vertical lines here, the two parallel lines, okay, are the same size. When we talk about a certain type of capacitor called an electrolytic or polarized capacitor, okay, we draw it a little bit differently. Okay, notice that one of those vertical lines has a curve to it, okay, and just by convention, the straight line is, okay, the positive terminal of the capacitor, which means that it must be connected to the positive side of the DC voltage source when you hook it up. Okay, and lastly here, the switch. Okay, a switch allows you to break a circuit and complete a circuit, and this is the way we draw a switch. And you'll notice here that, okay, the switch itself is in the open position. We typically draw a circuit, okay, with the switch in the open position, realizing that when it is closed, okay, then your circuit is activated. In this slide, we'll talk about various types of capacitors and show some examples and pictures of them. Some of these capacitors are, of course, very practical and used commonly in technology. Other ones are more theoretical that we will use to be able to, okay, discuss the physics behind capacitors and capacitance. So the parallel plate capacitor, extremely important. Okay, we will use this in our physics lab in order to study these properties of capacitance. And the parallel plate, okay, as the name suggests, consists of two parallel plates. Okay, remember, any capacitor is two conductors separated by an insulator. Here our two conductors are, okay, thin plates that are parallel to each other with an insulating material in between the plates. And we'll talk later on today, okay, specifically about this insulating material that we call a dielectric. What I'm showing you here is an example of a parallel plate capacitor. This is basically the computer key on your keyboard. Notice here that you've got your two conducting plates, and that in between the two plates is maybe some piece of foam which serves as an insulator dielectric. And when the key is pushed down, those two plates get closer together, and as we will see, that changes the property we call capacitance, which can then trigger, okay, a signal in the circuit. A tubular capacitor, which looks like this, is a much more common form of a capacitor. This is nothing more than a parallel plate capacitor, okay, made with two pieces of foil, typically metallic foil, very thin, with a piece of wax paper to serve as the insulator sandwiched in between them. So it's a form of a parallel plate capacitor that is rolled up so that it doesn't take up that much space. As we'll find out, okay, what makes a capacitor able to store more charge and electric potential energy, one of the factors is the plate area. So in this way, you can have a very large plate area, but by rolling it up, okay, it doesn't have to take up a lot of space. So these are, in a practical sense, much more common than your typical parallel plate capacitor. An electrolytic capacitor really is a tubular capacitor where the metallic foil is in contact with an electrolyte, okay, some sort of ionic compound in water solution. And when a current is applied, okay, to the conducting material, it causes oxidation of the metal. And that oxide coating on the foil serves as the insulating medium. The big advantage here is that oxide coating can be very thin, in which case, you can get these two pieces of foil, these conductors, to be pretty close to each other. And not only is it thin, so it doesn't take up a lot of space, okay, but in addition to being thin, that oxide coating can be a really, really good insulator. which, as we will find out, will mean that the capacitor can store more charge. So here's an example of an electrolytic capacitor, and you'll notice that in a practical sense, not when we draw it in a circuit diagram, in a practical sense, you'll notice that one of the prongs here is longer than the other, and typically, okay, the longer prong represents the side of the capacitor that needs to be connected to the positive terminal. Okay. A high voltage capacitor, certainly not used in integrated circuits, okay, typical electronics equipment, but okay, I'll show you a picture here and the inside of a high voltage capacitor. There are cases where these capacitors are, okay, structurally very sound. So you see they consist of many parallel plates here with some separation and a liquid oil, okay, to act as an insulating medium. So in cases where, okay, high voltages are used, okay, in electrical transmission, you would need to use one of these, okay, heavy-duty high voltage capacitors. Okay, typically the capacitors we're talking about here, used for electronics equipments, are typically not suitable for very, very high voltages. Now, these next two capacitors we'll talk about, these are what I would say are theoretical. The spherical capacitor, a central conducting ball, okay, surrounded by a conducting shell, okay, with a dielectric in between. I don't think this is ever practically used, but it makes for a nice problem because the geometry is so simple that we can easily calculate the electric field and the potential difference between the two conductors. So we'll take a look at this problem later, but just so you know, it's not a very practical type of capacitor. And similarly, the cylindrical capacitor here, where two conductors, okay, actually are in the form of two cylinders, okay, and we have some sort of dielectric material. So these concentric cylinders, okay, have an insulator in between them. And once again, okay, this is a nice, highly symmetric geometry, okay, but these types of capacitors are not super functional. They take up a lot of space. They can't store a lot of charge or electric potential energy, but they make a nice theoretical problem. All right, so not all capacitors are the same. And what we said that, one of the main purposes of capacitors is to be able to store charge and electric potential energy, okay, which can be quickly released to produce a lot of power. So this property we call capacitance is really a measure of a capacitor's ability to store charge and electric potential energy. So that's what we're going to be talking about in the next few slides. In this slide, let's take a look at what happens, okay, when you take a capacitor, an uncharged capacitor, and you hook it up to a source of voltage. And okay, we'll get a laser pointer here. So the capacitor becomes uncharged. This is our source of voltage. Okay, you recognize the circuit symbol here, and remember the large line represents the positive terminal, the small line the negative terminal. So when you initially hook up that capacitor, which is uncharged, well, what happens? Well, you see that, okay, this negative terminal of the battery, okay, has a certain electric potential, okay, whereas this conductor over here starts out uncharged, has no electric potential. So that electric potential difference between the battery terminal and this conductor on the right is going to cause electrons to start flowing to that conductor. And at the same time, simultaneously, when we look at the conductor over here on the left, okay, which is uncharged, okay, there is a potential difference between the positive terminal of the battery here and this uncharged conductor. That potential difference causes charge to flow. And since the charge carriers and metallic conductors are the electrons, okay, what happens then is that the electrons will leave, okay, this conductor here and flow to the positive terminal of the battery. Now the end result, if we look at this charge flow, is what we would call a complete circuit. Electrons flow from the negative battery to the conductor over here, and that electron flow continues, okay, from this conductor over here to the positive terminal of the battery. So we would say that, okay, and then within the battery itself, the electrons actually have to, some work has to be done by the chemical reaction to move an electron from the positive terminal back to the negative terminal so that the electron has taken a complete path. Okay, that's what we mean by a circuit. Now, as electrons flow through the circuit, when are they going to stop? Well, they're going to flow until this conductor over here is at the same electric potential, the same voltage as the negative terminal of the battery. And likewise, okay, electrons will leave this conductor on the left until, okay, the electric potential of the terminal, the positive terminal here, exactly matches that of this conductor. So when there's no longer potential difference, the flow of charge stops. So what we can say then is that when neutral conductors are connected to a source of electric potential difference, like a battery, they're going to become charged equal and oppositely. Okay, so however many electrons flow, okay, onto this conductor on the right, the same number of electrons will leave the conductor on the left, giving it a net positive charge. So the end result is that each of these conductors becomes charged equally and oppositely. You'll notice here that in the region between the conductors, okay, because of this charge separation, an electric field is established in that region. And we're going to talk in much greater detail about the properties of this electric field, okay, later. But for now, realize that, okay, there's an electric field established there, and as we will find out, okay, electric fields store electric potential energy. All right, so we can say then that, okay, when we have our capacitor in its fully charged state, okay, and I said this before, but we'll state it here, okay, then the potential difference provided by the source of power here, like the battery, will exactly match the potential difference of the capacitor itself. Okay, like we said, the electric potential of the negative battery will be the same as this conductor over here on the right. The electric potential of the positive terminal will be the same as the conductor on the left. Therefore, okay, you can reason that the potential difference, okay, of the capacitor will exactly match that of the power source. So in solving problems, you want to remember that. And finally, I just want to make a point that while each of these conductors becomes equal and oppositely charged, when you look at the net charge, okay, the net charge is zero. And this is really just a consequence of the law of conservation of charge. We can move charge from, okay, one place to another, and essentially that is what's happening here, right? If these conductors start out in an uncharged state, okay, we're basically, adding, X amount of negative charge to one conductor, okay, removing the same amount of charge from another conductor. So we may be transferring charge from place to place, but we are not creating any charge in this process. So when you add up the net charge of both of these conductors, the net charge will be zero, okay, which must be the case if charge is going to be conserved in this charging process. All right, so we'll now talk about the meaning of capacitance here and introduce units, okay, to be able to measure it. And I've alluded to this, I've stated this previously, but let's get this written down. So what do we use capacitors for? To store charge and electric potential energy. And the capacitance of a capacitor, this is a property of capacitors that measures their ability to store charge and therefore electric potential energy. And that electric potential energy is stored in the field between the charged conductors. By definition, this is made up. Okay, capacitance is a positive constant. It is simply the ratio of, okay, the charge that is stored on one of those plates. Notice I'm taking the absolute value here because, okay, it's a positive quantity here. So take, okay, the charge that is stored on either of those conductors, okay, but only the positive value, the absolute value, divided by the electric potential difference of, okay, your charged conductors. Now remember, we said that the electric potential difference of the capacitor will exactly match that of the source of power, okay, when it is fully charged. So this is a definition. It's important to memorize it, okay? And okay, a few things to note here. Okay, Q represents the magnitude of the charge on one of the conductors, not both. Remember, we said that the net charge of both conductors is 0. C is a positive constant. Okay, when we talk about units for capacitance, well, you may guess that in the SI system, when we look at our MKS units, we know the charge unit is the coulomb, and we know the unit for electric potential difference, okay, or electric potential, is the volt. So 1 coulomb per volt, okay, is our unit, but we give that a name. After, okay, the famous British scientist Michael Faraday, we call it a farad. So 1 farad, symbolized with a capital F, is simply 1 coulomb per volt. Now the truth is that a farad is a very large unit for capacitance. Not to say that we don't have capacitors, okay, in the 1 to many farad range. That's very true. But in the case of typical electronics components and integrated circuits, that is a very large unit capacitance. So we use our metric prefixes here to introduce some more common units that are used, okay, for electronic circuits, like the microfarad, the nanofarad, and the picofarad, sometimes called the puff. These are common units. Make sure you know those metric prefixes. So what sorts of factors affect the capacitance of a capacitor? We're going to be talking about that in great detail here. Okay, and remember, saying, you know, what affects capacitance? Really, what affects a capacitor's ability to store charge and therefore electric potential energy? As we will find out when we actually analytically calculate the capacitance for certain capacitors, we will see that certainly the size and shape of the conductors matters, okay, as you might expect. Okay, the separation of the conductors, really how far apart are they from each other, that will have an effect, as well as the insulating medium, what we call the dielectric, okay, that insulator between the two conductors will also play a role in how much charge and electric potential energy they can store. Now, in order to explore the various factors that will affect the capacitance of a capacitor, we need to, okay, use some physics to derive some theoretical expressions for the capacitance of capacitors, okay, to see how these factors come into play. That's what I mean by calculating capacitance analytically. Certainly we could do this experimentally. We could figure out, you know, how much charge is transferred to a capacitor, and, you know, measuring the potential difference of the charge capacitor, that's the same as a voltage source. That's easy enough to do. But that's not going to help us understand, okay, what's going on in that capacitor, what sorts of factors are affecting its ability to store charge. So we need to be able to do this analytically, and that's where we will turn to some of these, you know, fictitious, nicely shaped, highly symmetric capacitors, so we can calculate it. So we're gonna do this for a few different geometries, and this is the approach we're gonna take. All right, so we're gonna start by assuming that each capacitor plate acquires an equal and opposite charge Q. Okay, so we're going to assume that. Okay, we will then, using the physics that we've been talking about up to this point in the course, okay, we're going to calculate the electric potential difference as a function of charge here, okay, using what we've learned in the previous 2 chapters. So we will start by calculating the electric field between the conductors using Gauss's law. Okay, once we know what that electric field looks like, we can then calculate the electric potential difference between the charged conductors using our definition of electric potential difference. And once we know that, once we have an expression for the electric potential difference in terms of Q, then you will see that by taking the ratio using our definition of capacitance, okay, that the Q's will cancel out, and we should be left with, okay, just these other factors that will tell us something about the capacitance. So this is the approach that we're going to take here. So let's get busy. Okay, the first capacitor, and like I say, very simple geometry, but very important, okay, for understanding capacitors in this property we call capacitance, is the parallel plate capacitor. So remember, a parallel plate capacitor, we're talking about two conducting plates, two thin plates that are parallel to each other that are separated by a small distance. And you can see in the diagram then that, okay, there's a very uniform electric field established, okay, between these plates. So we're going to assume that the area of each of the plates is A, and that the distance between the plates is what we'll call D. So let's take this approach that we outlined on the previous slide. We're going to assume that each plate gets charged, okay, equal and oppositely, okay, with a magnitude of charge Q. We're now going to calculate the electric field, okay, between these conductors using Gauss's law. Now, we've done this previously, but hey, you can never get too much review here. So we'll quickly go through this process because we're experts at it by now. So the steps to be able to do this, you identify the symmetry of the charge distribution, which we would say is planar. Now we will ignore any fringing effects at the edges of the plate. So okay, we typically do that. If we are not near the edges, we can assume that we have this, okay, nice uniform electric field in the region between the plates. We're going to choose the Gaussian surface to match the symmetry of the charge distribution, okay, in order that the electric field will either be zero, okay, or constant on each part of the surface. And so, as we've seen previously, the Gaussian surface we choose is that Gaussian pillbox. Okay, it's a right circular cylinder, we'll say of length L and radius R. We draw the appropriate Gaussian surface so that it passes through the point where we need to evaluate the electric field, which is going to be in the region between the plates here. So let's draw our Gaussian surface here. And I just want to point out that previously, when we looked at applying Gauss's law, we started with the case of charged insulators, and we looked at a thin charged sheet, insulating sheet, and you'll notice that, okay, for that charged sheet, the electric field for a single sheet, the electric field, okay, went in both directions, really, radially away from the sheet. When we talked about a charged conducting sheet, okay, and we looked at the properties of charged conductors in electrostatic equilibrium, we also saw the same thing, that for a single sheet of charge, whether a conductor or insulator, the electric field went on both sides of the sheet. You'll notice here, though, that because we have two equal and oppositely charged conducting sheets, notice the electric field is restricted to the region between the conductors. In other words, there is no electric field, okay, that penetrates the top surface of this Gaussian cylinder, right? So that makes this a little bit different than what we've seen in the past. Okay, when you look at the flux here, the flux is really only through the bottom surface here. And you can easily see that there is no flux through the sides of the cylinder. So, as we know, this Gaussian cylinder really consists of three parts. It has a top end cap, a bottom end cap, and the sides, and there is flux only through the bottom end cap here. So, we're going to use the symmetry of the charge distribution to determine the direction of E on each part of the surface, and you can see it here. So, we will now, okay, evaluate the flux, continue on here in the next slide. So we'll continue where we left off on the previous slide here. we are now in a position to calculate the electric field between the conductors using Gauss's law, okay, by calculating the flux through our Gaussian surface. So, as we previously said, our Gaussian surface consists of three separate parts. Starting with the bottom end cap here, I'm showing you this infinitesimal area vector dA, which by definition is an outward pointing normal, and it is perpendicular to the surface. Notice here that the direction of dA is the same as the direction of the field itself. Okay, so we see that from our definition of electric flux here, take the magnitude of the electric field, magnitude of the vector dA times the cosine of the angle between them, which we said is 0 degrees. And as is always the case, okay, the electric field will be constant over any piece of the correctly chosen Gaussian surface. So at that bottom end cap, we can say that at all points there, the electric field has the same value, okay, in which case it can be taken outside of the integral, so that as we find, we simply sum up all the infinitesimal area elements to get the total area of that piece of our cylinder, which, okay, given a cross-sectional radius r, has an area pi r squared. So that is for the bottom end cap. Let's now turn our attention to the top end cap, and you'll notice here that the infinitesimal area vector dA I'm drawing as such. Notice that there's no field in that region, so there is no flux through that surface, through that top end cap, because there is no field there. The last piece we've got to look at is the sides of the cylinder. Let's take a look at the area vector dA there, okay, which I'm showing you. And here, as we alluded to previously, notice that, okay, the direction of dA is perpendicular to the field, in which case there is no flux of the field through the sides of the cylinder. So here, because the angle between dA and the electric field is 90 degrees, we get no electric flux. So the total electric flux through our Gaussian surface is the sum of the flux through each of these three pieces, which is the same as the flux through the bottom end cap. Now that we know the total electric flux through our Gaussian surface, we turn our attention to the charge enclosed by the Gaussian surface. Now notice here that, okay, the plates have a certain charge density. Each plate carries a total charge Q and has a total area given by A. So the surface charge density of the plate is this ratio Q to A. But notice our Gaussian cylinder does not enclose the entire plate. So we have to find out just the charge enclosed by our Gaussian cylinder, our Gaussian surface, will be equal to the charge density, sigma, okay, the surface charge density, times the cross-sectional area of our Gaussian surface. So here, sigma, the surface charge density, which we say is a total plate charge divided by the total plate area, times pi r squared gives us the cross-sectional area of just our Gaussian surface. So it's just the enclosed charge that counts. We're now in a position to equate, okay, the flux with the enclosed charge. Don't forget about this proportionality constant epsilon naught. When we equate those terms, we find out that, of course, we would expect that the cross-sectional area of our Gaussian cylinder doesn't come into play, it cancels out. Of course, the electric field should in no way depend upon, okay, a fictitious Gaussian surface that you choose. So what we find here is that, okay, the electric field in the region between these conductors is Q over A. Okay, that is just sigma divided by epsilon naught. Now recall, when we completed our unit on conductors in electrostatic equilibrium, remember we said that for a charged conductor, where we know that all the charge must reside on the surface of that conductor, we said that at the surface of that charged conductor, the charge density at any point was equal to sigma over epsilon naught. Okay, well, we pretty much just proved that here for this special case of two charged conductors. Okay, we're showing that the electric field, okay, for these conductors is given by this expression sigma over epsilon naught, as we would expect. So from here, we need to calculate the electric potential difference between these charged conductors. To do this, okay, we talk about moving a charge from, okay, one plate to the other. Okay, the direction that we travel doesn't matter. I'm going to arbitrarily say that let's move a small increment of charge from the upper plate to the lower plate. Since we divide through by the charge, we get a charge independent quantity. We just have to make sure the charge we move, okay, is small enough that it doesn't affect our charge distribution. So when we write this definition for electric potential difference for our particular arrangement here, okay, the magnitude of the electric field, which is just Q over A epsilon naught, okay, the magnitude of this displacement vector ds times the cosine of the angle between them. Notice that with my choice of integration path here, ds, that infinitesimal displacement vector, is in the same direction as the field, okay, in which case we're taking the cosine of 0. And any constant can be taken out of the integral, QA epsilon naught, those are all constants, we take them outside. When we, okay, sum up the magnitudes of these little infinitesimal displacements, what do we get? We get really the total distance between the two plates, right? That is just the magnitude of the total displacement from the upper plate to the lower plate, which we said we give a name, d, representing the separation distance of these two conductors. So there is our expression for electric potential difference. We are now ready to calculate the capacitance by taking this ratio. Okay, notice we take Q, divide by our expression here, which is, we make positive, right? Okay, we take the positive value here, and when we take that ratio, we see that the Q cancels out, and this is what we are left with. Okay, epsilon naught A over D. Now take a look at this. Okay, this should make a lot of intuitive sense to you. Okay, if the capacitance of a capacitor measures its ability to store charge and electric potential energy, what we find out here is that certainly the size and shape and arrangement of these conductors matters. Does it make sense that the capacitance increases with plate area? Sure, the greater the plate area, the greater the amount of charge that can be stored on them, okay, and therefore the greater the electric potential energy, okay, that will be stored in the field between them. So yeah, we would expect a direct relationship between plate area and capacitance. Okay, as we'll find out here, this factor D, there's an inverse relationship between the separation distance and the capacitance. Does that make sense? Well, as we'll find out, okay, as these conductors get further apart, okay, the field and therefore the electric potential energy stored in between those plates is going to decrease. So again, this physical constant here, both A and D represent, they tell us something about the arrangement, the geometry of our capacitor, and therefore its ability to store charge and electric potential energy. The next slide is a simulation. I'm going to show you a simulation. We'll take a look at some of the properties that we've talked about up until this point for a charged capacitor, and look at these two properties as well. Okay, look at both the area, the effective area on capacitance, as well as the plate separation.
In this simulation of the parallel plate capacitor, notice that we're starting with the capacitor in its uncharged state. Notice the battery voltage is 0. First thing we'll do is we will connect the leads of our voltmeter, okay, to the bottom and top plate of the capacitor, so that as the battery voltage increases, okay, we can see what the voltage is on each plate. So what we're going to do, like I said, we start with the capacitor in its uncharged state. We're going to gradually increase the battery voltage up to its maximum value of 1.5 volts. And I want you to take a look at what happens to the charge on both the bottom and the top plate. Notice what happens to the sign of the charge as well as the magnitude of the charge on each plate.
Also notice at the top hand portion of your screen here, okay, the simulation gives us a measure of the capacitance of the capacitor here. So let's gradually increase the battery voltage from 0, okay, up to its maximum value. You will notice here that as we do this, okay, the charge on each of these plates increases. You will also notice that the top plate, which is connected to the positive terminal of the battery, acquires a net positive charge, whereas the bottom plate connected to the negative terminal of the battery acquires, okay, a net negative charge. So as we increase it up to its maximum value, also notice here that, okay, the capacitance, okay, of this capacitor does not change. Okay, while the charge does, and the voltage increases, the capacitance does not. Remember that okay, the capacitance is really a measure of, okay, the geometry, that is the size and shape and separation of the conductors themselves, as well as any insulating medium that happens to be in between. And we'll talk a lot more about that later, okay, in part 2 of this okay, this lecture. What I now want to take a look at is how changing some of these geometries, like the plate area and plate separation, will affect, okay, the capacitance of the capacitor. So let's keep our capacitor charged at with this voltage of 1.5 volts. Okay, and we will start here by changing the plate area. And let's see what happens here, okay, to the capacitance here. So as I decrease the plate area here, okay, you will notice that not only does the capacitance decrease, okay, but the charge that each plate is able to store decreases as well. Remember that capacitance is a measure of a capacitor's ability to store charge. So changing the plate area changes the total amount of charge that can be stored on each of the plates. Okay, you'll notice here that as we did that, okay, as we decrease the plate area, okay, notice that the voltage, okay, did not change. Okay, the voltage of the plates remained constant, okay, but both the capacitance and the charge stored on each plate changed. Let's now take a look at this other factor, the separation distance. So as we increase, okay, the distance between these two plates, notice what happens here to the amount of charge stored on each plate as well as the capacitance. The amount of charge drops, it decreases, and therefore the capacitance of the capacitor decreases, okay, as we increase the plate separation. Once again, you will notice that the voltage, okay, between these two plates, the electric potential difference does not change at all. That stays constant, but increasing the separation distance of these two plates lowers the capacitance and lowers the amount of charge that can be stored. Okay, the last thing we'll take a look at, I'm going to check this electric field box here so we can see what happens, okay, to the field between the plates as we change some of these factors here. So as I move these plates closer together, okay, you will notice that that electric field between the plates increases. Okay, and we say that ultimately it's electric potential energy that is stored in that electric field. So when we increase the capacitance between for this parallel plate capacitor by bringing the plates closer together, okay, we are also increasing, okay, the electric field in between those plates as we increase the amount of charge, okay, that can be stored on each of those plates. In this demonstration, we will take a look at the effect of plate spacing on the capacitance of a parallel plate capacitor. So in order to do that, you'll notice that I have one of the plates of the capacitor connected to this electroscope. The reason for that is we can see
by what is happening with the leaves of the electroscope, okay, whether they fall or whether they move apart, that tells us something about the charge on the plates of the capacitor. When I charge up this system here, okay, the electroscope and the plate that is connected to, that charge should remain roughly constant. So what we can infer is that the more charge there is on the electroscope, which would make the leaves diverge, the less charge will be on the capacitor plate. So this is the way we're going to measure how much charge we actually have on the capacitor plates. Now, let's think about what we know, right? We know that the charge on one of these capacitor plates goes like, or is equal to the capacitance times the potential difference. What I'm going to do is I'm going to change the capacitance. I'm going to move the plate here closer to the other plate. As the plate spacing decreases, the capacitance should increase. That should increase the charge on the capacitor plate, which should decrease the charge on the electroscope. So in that case, you should see the leaves of the electroscope start to fall. So let's charge up the system here. Okay, and of course, you know, it's not going to maintain a constant charge forever. And we will see that as I move this capacitor plate closer to the other ones, the plate spacing goes down, the capacitance goes up. Therefore, the charge on the plate, the capacitor plate, should increase. Okay, and that's why we see the electroscope leaves collapse. When I move the plate, okay, in the opposite direction, the plate spacing increases, the capacitance goes down. That means that the charge on the plate goes down, more charge is on the electroscope, okay, and that is why the electroscope leaves diverge, why they go apart.
We'll take a look at one more example where we calculate the capacitance of a certain geometry capacitor in an analytical fashion. So we can take a look at how, okay, certain factors like the size, the shape, the separation of the conductors will affect the capacitance, affect the capacitor's ability to store charge and electric potential energy. The case of the cylindrical capacitor, it's a good problem. It's in the text. We can't do everything, so you can check out that on your own. I'm going to choose to talk about the spherical capacitor because at the very end I want to look at, okay, how we can calculate the electric potential for an isolated charged sphere. Believe it or not, this is a problem that you saw previously in the course already, and I want to call your attention to that. So let's start with the spherical capacitor. So we have two conducting spheres. Okay, they are concentric. We'll say the inner sphere has radius A, the outer sphere radius B. They're charged equally and oppositely. It doesn't really matter which one is charged which way. Okay, I put the inner sphere of smaller radius with a charge of plus Q, outer sphere with the larger radius charge minus Q. And okay, given that, we will go through the process we went through previously, right? We assume Q, we assume that we have equal and oppositely charged conductors. And in calculating the electric field, okay, between these conductors, we can use Gauss's law. Now, in this case here, we're going to use a previous result. Let me show you what the field looks like. We looked at the case of what the electric field looks like for a spherically symmetric charge distribution. This is when we applied Gauss's law previously. And just to say a few things, notice that if we want to find what does a field look like in this region between the two conductors, if we put a Gaussian surface there, notice that that Gaussian surface is enclosing, okay, a charge distribution that is spherical, has a charge Q, and we showed that, okay, the electric field for a spherically symmetric charge distribution, when you look outside of the sphere, okay, is identical to that of a point charge. It's identical to placing, okay, a point charge plus Q at the center. Okay, the field looks no different. Now, if you're inside of the charge distribution, that's a different story. Okay, but the region where we're evaluating the field here is outside of, okay, that inner sphere of charge Q, so we know that the direction of the electric field is radial, okay, expressed by this unit vector r hat, and the magnitude of the field in that region, okay, is given by the electric field of a point charge, okay, Coulomb's law constant times, okay, the charge of that inner conductor divided by r squared, where r squared is the distance between the center and the field point, okay, somewhere in this region between the two conductors. So given that, okay, we can now calculate the electric potential difference, okay, between these two charged spheres. And in so doing, we can choose our integration path. We will move from inner conductor to outer conductor from, okay, radius r sub a to r sub b, and in doing so, you'll notice that our infinitesimal displacement vector ds is in the same direction as a field, in which case we get this cosine zero factor. Evaluating the integral, okay, very simple polynomial integral of r to the minus 2 dr is simply r to the minus 1 divided by minus 1, and when we plug in our limits of integration, okay, from a to b, okay, that gets us to this point here, okay, q over 4 pi epsilon naught 1 over b minus 1 over a. Now, okay, you will notice here, okay, that that I've chosen to write this a little bit differently. It's going to make our calculation of capacitance look a little bit different, but I've chosen to, instead of write it like this, I've gotten a common denominator, AB here. Okay, so when we take the next step and calculate the capacitance here, remember this, A minus B in the numerator here is going to be a negative value, but when we take the capacitance, we make it positive. Okay, so we'll take the absolute value of that. And you see here that the Q's cancel. Using this approach, that always happens. And this is the result we end up with here for the capacitance. I want to point out here a couple things. Okay, first of all, does this value for capacitance make intuitive sense? Well, it should. Okay, because just as we saw for the parallel plate capacitor, that the capacitor was directly proportional to the plate area, we find out here that the capacitance is directly proportional to both the radius A and B. Do you realize that the area of each of these spheres is, okay, going to be proportional to that radius? And so the bigger the radius, okay, of each of these spheres, the more charge that can be stored on each of them. So again, we find out that the capacitance, which is a measure of how much charge can be stored on these conductors, is directly proportional to the plate area, okay, or in this case here, the product of the two radii, okay, A and B. Also for the parallel plate capacitor, we showed that the capacitance is inversely proportional to separation distance, right? The distance between the two parallel plates. Well, do you see here you have the same relationship here? A minus B, okay, that gives us the separation distance between these two conductors. And as we said, it would make sense as that separation distance increases, okay, the electric field and the electric potential energy stored in that region would decrease. Same as for the parallel plate capacitor. All right, so given that, I want to take a look at what would happen if we had an isolated sphere, okay, only one conductor. Well, we can still take the same approach here. Let's go through the calculation, and then I'll point to the significance of the result here. But for an isolated sphere, remember we use the convention that the electric potential is zero when you're infinitely far away from the charge distribution, so at a position of infinity. So here, when we want to apply our definition of electric potential difference here, okay, we choose the integration path to go from infinity all the way into the charge distribution, having the radius A here. So our integration path from infinity to A would be in this direction. Notice it's opposite the field, so that's why this expression looks almost identical here to this one here. Okay, of course our limits of integration are different, right? We're going from infinity to A. and the cosine zero factor gets replaced by cosine 180. Okay, why? Because in this case, okay, when we looked at our integration path here, okay, we were integrating from, okay, we moved from sphere A to sphere B in the same direction as the electric field. Now we're moving from infinity to, okay, sphere A, opposite the direction of the electric field. So that's, okay, hence the cosine 180 factor. So when we evaluate this, okay, we know that 1 over infinity is 0, and this is the answer that we end up getting. So I want to point out here, okay, that when we calculate the capacitance here, taking that ratio, believe it or not, this expression you've come across before. Do you remember when you did the lab on Coulomb's law, okay, where you needed to find out, in the Coulomb's law apparatus, which was this torsional pendulum, you had those conductive spheres. One was attached to the torsion wire, one you brought in close to it. But we said that we needed to figure out what the charge was on a conductive sphere. And we said that the charge on the sphere was directly proportional, okay, to the voltage of the sphere. And we used a proportionality constant, 4 pi epsilon naught A. Believe it or not, okay, without knowing it at the time, that proportionality constant was simply the capacitance, right? Okay, we showed that, okay, really the greater the radius of that sphere, the greater the capacitance. It could absorb more charge. I mean, that should make sense. So at the time, you just treated this as a proportionality constant, when really what you were really doing was multiplying, okay, the voltage of that sphere, which was measured by your voltage source, okay, times the capacitance of that charged sphere. We'll now turn our focus on the use of capacitors in circuits. Now, analyzing electrical circuits is a huge topic, okay, a topic for which, okay, many courses exist for engineers. Okay, but a topic that we're going to briefly touch upon in this class. So in order to analyze circuit behavior, we invent this fictitious quantity, in this case here, in the case of capacitors, what we call equivalent or effective capacitance. And as we will see, this allows you to deconstruct a circuit and be able to find out, okay, various properties of this circuit. Okay, like charges of individual capacitors, or, okay, voltages of individual capacitors. So in this unit we're talking about capacitors, but in a couple of weeks we'll be talking about a different circuit component that we call a resistor. And the concept of effective or equivalent capacitance, okay, will be replaced with the concept of equivalent or effective resistance. So the basic idea behind the concept, it's quite useful, and it's a concept that we'll return to as well. So let's take a look at what we mean here. So basically we're saying that the equivalent capacitance for a combination of capacitors in a circuit would be the capacitance that of a single capacitor that could replace all of the capacitors in the circuit without changing the physical behavior of the circuit. So while you have a real circuit consisting of n capacitors, we are trying to figure out how could we replace those n capacitors with a single capacitor having a capacitance value we call the equivalent capacitance, so that, okay, the behavior of the circuit wouldn't change. In other words, okay, the total voltage of the circuit would be the same, okay, the total charge of that circuit would be the same. So if we could do that, if we could replace a circuit of n capacitors with a single capacitor, then what we could say is that, okay, the total charge okay, for our single capacitor circuit would be equal to this single capacitor having a capacitance value, okay, we call the equivalent capacitance times delta V total, where that is, okay, the total voltage provided by your voltage source. So like I say, this is an analytical technique. We are doing something imaginary or fictitious here, but it happens to be quite useful in being able to analyze a circuit. So we'll see how this is employed, okay, in the next couple of slides. With the definition of equivalent capacitance, sometimes called effective capacitance, in mind, okay, in this slide we're going to turn our attention to how capacitors can be arranged in circuits. Okay, specifically we'll talk about a series arrangement and a parallel arrangement. We'll compare and contrast, okay, different properties of these two arrangements, and at the end of the slide we'll come up with an expression for how to calculate the equivalent capacitance for each of these arrangements. So when it comes to solving problems here for the homework, what we're going to talk about on this slide, these results, okay, the theory is extremely important. Okay, this is what you have to apply, okay, when you get to those problems. Okay, what we're going to talk about in this slide. So first of all, let's talk about, okay, these two arrangements. We arrange capacitors in series, okay, and I will look at the simple case of two capacitors here. Let's say if each with a capacitance C1 and C2 connected to some source of voltage. Okay, you will notice here that what makes this a series arrangement is that there's only one path for charge to flow in the circuit. Now, when we look at charge leaving, let's say an electron leaves the negative terminal of the battery here and flows on to the left-hand plate of capacitor C1, okay, and we said that, okay, charging that plate negatively, we say an equivalent amount of electrons leave the right-hand plate of capacitor C1, okay, and leaving that with a net positive charge. Those electrons flow onto the left-hand plate of capacitor 2, in which case an equal amount of electrons will leave the right-hand plate of capacitor 2 and wind back at the positive terminal of the battery. Do you see that in this process here, there is only one pathway for electrons to travel in this circuit? Let's contrast that to a parallel arrangement here. Okay, so if I take my two capacitors and I arrange them in parallel, then we see once again we have the same voltage source here, okay, which is providing that, okay, that electrical pressure to push charge through our circuit. But in a parallel arrangement here, you'll notice that when we once again trace the path of electrons leaving the negative terminal of the battery here, okay, I'll trace that path with my laser pointer here. When the electrons get to this point right here in the circuit, this is what we call a junction point or node. Notice that those electrons now have a choice. They can move to the left and go to capacitor 1, or they can move to the right and go to the top plate of capacitor 2. There is more than one path for those electrons for that charge to take. Okay, and this is what makes for a parallel arrangement. Now, when it comes to talking about the potential difference, okay, for a combination in a series and parallel arrangement, let's start with the series here. And I want to just point out here, and we'll return to this idea later, that if we trace the path of a charge and we look at what's happening in the circuit in terms of energy, and I'm going to start with an electron here at the negative terminal of the battery. As that electron moves through the circuit onto the left-hand plate of capacitor 1, okay, and we say that an equivalent number of electrons leave the right-hand plate of capacitor 1, okay, and move on to the left-hand plate of capacitor 2. When that happens, there is a change in potential energy here of this capacitor. That charge separation, okay, brings about a change in potential energy across this capacitor. Likewise, when those electrons that have collected on capacitor 2, we say the same number of electrons leave the right-hand plate of capacitor 2, so that once again, this capacitor becomes equal and oppositely charged. Okay, once again, that represents a change in potential energy across capacitor 2. And that change in potential energy, according to the law of conservation of energy, okay, energy is not created or destroyed. So what happens when that electron gets to the terminal of the battery here, then the battery has to do work on that electron, which has now lost potential energy. Usually it does work in the form of a chemical reaction to bring that electron back, moving it to the other terminal, to the negative terminal where it started, to give it the same amount of potential energy it started with. So what we can say is that the potential energy for a complete path, for a complete circuit, the change in potential energy, okay, for the voltage source must be equal to the loss of potential energy across each capacitor when we sum up those changes in potential energy. So this is how we get this arrangement here, right? This is a statement of the consequence of the law of conservation of energy, right? We're not creating or destroying energy. We're saying total potential energy change provided by the source, okay, that is a difference in potential energy between the negative and positive terminal, must be equal to the sum of the changes in potential energy across each of these capacitors due to the charge separation that comes about. Now, you know that potential energy and change in potential energy is related to electric potential difference according to this equation here. So, given this, we can see that the total change in potential energy provided by the source given by Q delta V total must be equal to, okay, the sum of these expressions for the potential energy change for each capacitor. We can divide through by this common factor of Q, in which case we find out that the total electric potential difference provided by the source is simply equal to the sum of the electric potential differences of each of the capacitors in the series arrangement. So remember this result, folks. This is very important to remember, okay, for the series arrangement of capacitors. You're going to be using this when it comes to problem solving. When we look at the parallel arrangement here, okay, I want you to notice here that if I look at the negative terminal here, you notice that it is electrically connected to the top plate of each of those capacitors. That tells you that the top plate of capacitor 1 and capacitor 2 is at exactly the same electric potential as, okay, the negative terminal of the battery. Likewise, the positive terminal of the battery here, okay, is electrically connected to the bottom plate of each capacitor. So that tells you that the bottom plate of each capacitor is at exactly the same electric potential as the positive terminal of the battery. What that tells you then is that the potential difference across the source of voltage of the battery must be exactly equal to the potential difference across each of those capacitors. So this leads to this result here, that the total potential difference provided by the source, okay, is exactly the same as the potential difference, okay, across each individual capacitor. Now, when it comes to charge here, and going back to the series arrangement, just like we said, if we look at the charging process, electrons flow from the negative terminal onto the left-hand plate of capacitor 1. Okay, when that happens, that plate acquires a negative charge. Likewise, okay, electrons from the right-hand place of capacitor 2 flow from there, really the same number of electrons, to the positive terminal of the battery. So each of these outer plates gets equal and oppositely charged. Once that happens, that's going to induce an equal charge on the inner plates, right? Like we said, that's going to force electrons to move from, okay, the right-hand plate of capacitor 1 to the left-hand plate of capacitor 2, okay, until we have those plates equal and oppositely charged as well. So what we can say here then is that, okay, the charge of each of these capacitors, capacitor 1, okay, is exactly the same as the charge of capacitor 2, which is exactly the same as, okay, when we talk about our expression for equivalent capacitance, that would be the same as the charge that would go on a single capacitor that could replace the combination. Okay, so we're saying that, you know, each capacitor requires the same charge on each plate, and for a okay, when we look at the single capacitor to replace the combination of capacitors for the equivalent capacitance, okay, we can say that the charge on that capacitor will also be the same as any individual capacitors. Now, when we look at the parallel arrangement here, okay, and we're talking about charge, like we said, when charge leaves the negative terminal of the battery and comes up here to this junction point, okay, some of that charge is going to go to capacitor 1, some of it's going to go to capacitor 2. So there's no reason why the charges would be the same. Remember, what does capacitance measure? A capacitor's ability to store charge. A capacitor with a higher capacitance will be able to store more charge, so more charge will flow onto that capacitor. So basically, the charge won't be the same on each capacitor, but we can say from our definition here of capacitance that the charge on each capacitor will be equal to its capacitance times, okay, the potential difference, which, remember, we did say was the same, okay, for every capacitor in parallel. Okay, so charge will not be the same for a parallel arrangement, okay, but we can say then that, okay, the total charge that leaves our voltage source here, okay, according to the law of conservation of charge, that charge has to go somewhere. The total charge leaving the source will be equal to the total charge that ends up on the plates, which would be equal to charge of capacitor 1 plus capacitor 2, and so on. And, you know, equivalently, when we talk about an equivalent capacitance, we can then say that this Q total not only represents the capacitance of the charge of the leaving the source of voltage. When we replace this combination with a single capacitor, we can say that that also represents a total charge on that single capacitor. So, okay, here we have the expression here, okay, for the parallel arrangement, right? That the total charge, okay, that leaves your source of voltage will be equal to the sum of the charges of each on each capacitor, which you can figure out using this expression C delta V. Now, in deriving an expression for the equivalent capacitance here, okay, for the series arrangement, we're going to start with the law of conservation of energy here, okay, which is what we derived up here. And when we say that, you know, okay, according to that law, we showed that, okay, the total potential difference provided by the source is the sum of the potential differences across each capacitor. And when we use our relationship here, Q equals C delta V, okay, we can write that in terms of Q and C. So here, remember, delta V total, this would be, if we could replace this combination of N capacitors with a single capacitor, so there's only one capacitor, it would have a capacitance C equivalent. And remember, the charge on that capacitor Q, what we're saying above here is it would be the same as the charge on any individual capacitor. So do you see where this comes from here? That charge on the single capacitor replacing the combination divided by the equivalent capacitance of that single capacitor must equal, okay, the sum of these terms here when we take out the common factor of Q. This is the expression we get for the equivalent capacitance, right? We write it as a reciprocal. We'll show you for a combination of two capacitors, you can solve this for C equivalent as, okay, the product of your two capacitances divided by the sum of the two. Moving to the parallel arrangement here, okay, here we're going to, okay, incorporate the law of conservation of charge. Start there. Say the total charge, okay, on that single capacitor that could replace the combination, which is the same as a total charge that would leave your source of voltage to go onto all of the plates, okay, would be equal to the sum of the charges of each of the capacitors. And once again, using the definition charge equals capacitance times potential difference, okay, we can say that total charge, okay, would be equal to the capacitance of the single capacitor replacing the combination times that total potential difference, which, okay, using what we showed above here, would be the sum of these terms here. And since we know that the potential difference, okay, for any capacitor is the same as the potential difference of the source, okay, we know that delta V is the same. We can cancel that out of all the terms, in which case we find out that our expression for the equivalent capacitance of a parallel arrangement is just the sum of the capacitance of the individual capacitors. So let's finally ask ourselves, does this result make sense? Well, it should here. Okay, when we look at the equivalent capacitance for the series arrangement, adding capacitors in series, okay, causes the overall or equivalent capacitance to decrease. Think about what you know about the parallel plate capacitor. When we place capacitors, every capacitor we add to our circuit, think about what it does to the effective plate spacing. Every time you add a capacitor with a spacing, you are increasing the average, or let's say effective, plate spacing of that single capacitor that can replace a combination. And we know that there's an inverse relationship between, okay, plate spacing and capacitance. So adding capacitors in series increases the effective plate spacing of that equivalent capacitor, which will cause the capacitance to decrease. Okay, contrast that to the case of the parallel arrangement. When you add capacitors in parallel, okay, what are you effectively doing? Okay, you are effectively increasing the overall or average plate area. Okay, so having two capacitors in parallel here, okay, basically this plate area plus this plate area, it's as if we're increasing the effective plate area. These are both at the same electric potential. So we can look at it this way to say that, okay, for a parallel arrangement, increasing that effective plate area, when you look at this expression we derived previously, okay, should increase the capacitance. It should increase the amount of charge and potential energy, okay, that can be stored in the capacitor.
In this demonstration, we are going to experimentally verify this concept of equivalent capacitance for both a series and parallel combination of capacitors. So we're going to start out here by experimentally determining the capacitance of the two capacitors we're going to use with our capacitance meter. So our first capacitor here, hooked up to the meter, gives us a value of 4.30 microfarads. So we'll remember that number, 4.30. We will get our second capacitor, which I've put some tape on so we can keep it straight. And we will make a measurement of the capacitance of this capacitor, which is 4.14 microfarads. So we've got capacitor 1, 4.30 microfarads, capacitor 2, 4.14 So now that we know the experimental value for the capacitance of each of these capacitors individually, okay, we will take a look at the combination of these capacitors in both a series and a parallel arrangement. Starting with the parallel arrangement, okay, we are going to theoretically determine the equivalent capacitance of the combination. And you recall that when we talk about the equivalent capacitance, we're talking about the value of the capacitance of a single capacitor that could replace the combination of capacitors in the circuit. So you recall that for a parallel arrangement, we find the equivalent capacitance by taking the simple sum of the capacitances of the individual capacitors. In our case, we're only talking about a combination of two capacitors. So, okay, when we take the sum here, we're talking about, okay, adding 4.30 microfarads as capacitance to our first capacitor to 4.14 microfarads, which represents the capacitance of the second capacitor. And when we do the arithmetic here, okay, this gives us, okay, 8.44 microfarads. Okay, that is the equivalent capacitance, in theory, okay, of the combination of capacitors. What we now want to do is actually experimentally measure this and see if this theory is indeed correct. So to do that, we'll use our capacitance meter here, and we will hook one of our leads to, okay, one side of capacitor 1, hook the second lead to the other side of capacitor 2. So we're making a measurement across the combination, and we see here that we get, okay, looks like 8.31, okay, for the measured value, okay, of the capacitance of the combination. So there's a slight difference, but that's pretty close, okay? There's certainly some experimental error here, okay, but we can, hopefully you would agree that the theory does work. So we can now take a look at the series combination of these capacitors. What you now see in front of you on the desktop is a series arrangement of these two capacitors. And remember that for a series arrangement, okay, there's only one pathway for charge to take, as opposed to the parallel arrangement where we have this branching effect and there's more than one path that charge can take in moving through the circuit. So we will, just like we did for the parallel arrangement, we'll start out by calculating the theoretical value for the equivalent capacitance of this series arrangement of two capacitors. And you recall that the calculation is slightly more complicated. Okay, but for two capacitors in a circuit, we have this handy-dandy formula here. We can say the equivalent capacitance is found by taking the product of the two capacitors divided by the sum. So when we plug in our numbers here, we've got 4.30 microfarads times 4.14 microfarads divided by the sum, which we already found over here to be 8.44 microfarads. And when you do the number crunching and you punch the numbers in a calculator, the value you actually get here is going to be 2.11 microfarads. So that's a theoretical value for the equivalent capacitance. Let's now measure the value, find an experimental value and see how close we are. So we will stick one lead to our capacitance meter to one side of our circuit, the other lead to the other side here. And here, we come up with a value of 2.09 for a measured value. So certainly within experimental error, you can see that the measured value is pretty close to what we predict using this formula we derive for the equivalent capacitance.
All right, so when it comes to solving circuit problems with capacitors in series or parallel arrangements or a combination of both, okay, very often what you're asked to find will be a specific capacitance of one of the capacitors in your arrangement, okay, like if it's not given to you. You might be asked to find a charge of some given capacitor in your arrangement, or maybe even the potential difference across that capacitor. So in order to do that, okay, a general approach means that usually what you want to do is you want to start by finding the equivalent capacitance of your circuit. And by doing that and using what we talked about on the previous slide, okay, you can very often try to reduce your circuit and maybe figure out a potential difference for a piece of your circuit using this concept of equivalent capacitance. So in this slide, what we're going to do is we're going to start there and take a look at how to calculate the equivalent capacitance, okay, for a combination of capacitors. And remember that when you know that equivalent capacitance, what you're saying is that the total potential difference, okay, for that single capacitor with a capacitance equal to the equivalent capacitance, that total potential difference, okay, times that equivalent capacitance will be equal to the total charge that you would find on that single capacitor. That will also be the total charge that leaves the source of voltage in your real combination of capacitors. So, all right. In this problem here, we're told that all of these capacitors are equivalent, so they have the same capacitance C. And we want to remember our goal is to replace this combination of 6 capacitors with a single capacitor having a value of capacitance we call the equivalent capacitance, such that, okay, we don't change the physical behavior of our circuit. So how do we do this? Okay, well, typically you want to kind of start with your innermost branching and you want to work your way out. So, and generally speaking, there's more than one way to go about solving these problems. But if you look at this combination here, and I'm just going to start with this branch here. It looks kind of like the innermost most complicated part here. So when I look at this, I see that I have 2 capacitors in parallel, okay, and we're going to reduce this bit by bit. Okay, I can take those 2 capacitors in parallel and I can replace those 2 capacitors with a single capacitor here, okay, that would have an equivalent capacitance of those 2 in parallel. Well, we know from the previous slide that when you have capacitors in parallel, you find the equivalent capacitance by simply taking their sum. So the capacitance of this single capacitor replacing the combination would be 2C. Likewise, okay, I can look at this parallel combination here and I can do the same thing. I can say that I can replace those 2 with a single capacitor having a capacitance of 2C. So we're making progress. We've reduced our 6 capacitor circuit to a 4 capacitor circuit. From here, you'll notice that on this top branch here, these 2 capacitors are now in series. So I can, once again, try to replace those 2 capacitors with a single capacitor having a capacitance equal to the equivalent capacitance. And I'll just tell you this here, that if you take your 1 over C equivalent equals 1 over C1 plus 1 over C2, and if you solve that, okay, this is kind of a nice result here, that equivalent capacitance is the product divided by the sum. Only true for arrangement of 2 capacitors, okay, in series. So I'm going to take the capacitor, this capacitor here, which is C, multiplied by, okay, the capacitance of this capacitor here, 2C, and I'm going to divide by the sum of the capacitance, gives me a capacitance of 2/3 C. So, okay, I can now replace, okay, that combination of 2 capacitors with a single capacitor having a value of 2/3 C. And likewise for this bottom branch here, okay, same physics here. I can do exactly the same thing. So I've now reduced a 6 capacitor circuit to a 2 capacitor circuit Notice here that these two capacitors are in parallel, so I can now reduce the combination of two to a single capacitor, okay, by using this concept of equivalent capacitance, where we simply add the capacitances, and that is going to get me, okay, 2/3 C plus 2/3 C is 4/3 C. So this is the equivalent capacitance of the entire combination of 6 capacitors. Knowing that, okay, it depends what the problem asks you to find, but that's a place to start. I can now find the total charge that moves on all of the capacitors, okay, from the voltage source here. Okay, I know, you know, the potential difference across that single capacitor is the same as that provided by the source. Okay, so using what we talked about on the previous slide, okay, that's how we kind of work our way through a circuit to find out whatever it is we're asked to find.